I want to look at another version of Prim's algorithm. So before I start this new version, were there any questions about the versions of Prims and Kruskal's that we did last week? Kruskal's just sorts edges, and then you add them in whatever lowest to highest weight order they occur in. Prim requires that you add adjacent edges, edges that are incident to one of the vertices you already selected. The problem with both of these versions of these algorithms is they were very visual. This is the same graph we were using last Monday. I want to do something that isn't visual, that I can do algorithmically, that I can make decisions on in a way that throws out looking at the picture. To do that, I need a matrix. Now, I apologize in advance for using D and not meaning diagonal. For those who are in linear, D almost always means a diagonal matrix. Here it means a distance matrix. So I want you to create an n by n matrix where n is the number of vertices. And let's say that the ijth entry is the weight of the edge connecting I and j. Where if there's no edge, you write a 0. Now that means for this matrix, you're building, for this example graph, you're going to build me a 7 by 7 matrix. And every number in it, the weight, you see up there, or a 0. Those are only choices. Please make this particular matrix. Note that since D is not directed, this is a regular simple graph. This is an ordinary simple graph. I don't want to use regular. That word has meaning. Since this is an ordinary simple graph, what kind of a matrix will you get? Yes, that's the size based on the number of vertices. But what property will this particular matrix have? What must it have? Reese?
It's going to have zeros on the main diagonal.
Yes, because there are no loops. What other property must it have? It must be symmetric. Because ij and ji have the same weight, therefore those entries in the matrix must be the same. So I'm going to get a symmetric square 7 by 7 with zeros on the diagonals. You know what? You zeroed the wrong number. Let me think on this for a second. If there's no edge, I can't get there in one step, right? If I write a 0, it seems to me that that makes that edge free, doesn't it? Free is always cheap, isn't it? That's not a good thing. Let's change that symbol. Instead of 0, make it infinity. We want that weight to be really, really big because we're going to try and select low weights. So let me just change that from a 0 to an infinity. A is only adjacent B and D. Here's our distance matrix. Now, again, depending on the version of the algorithm you look up, I saw one version that instead of using infinity on the diagonals, it used zeros, because if you're at vertex A, it costs you nothing to go nowhere. But you're not moving anywhere, right? And technically, there is no loop at A or C or D or wherever. So I like the idea of using infinities instead. And another version of the algorithm had dashes instead of infinities. You can't get there from here. There's no entry in this matrix. I suppose if you were coding it, you could fill that part of the array with nulls. Wouldn't matter. But then a null and a zero would be distinctly different in this location. How did Prim's algorithm start? The cheapest one, what? Technically, that's how Krustal started. Because in Krustal's algorithm, we sorted the edges from smallest to largest first. But in Prim's algorithm, we didn't start with a choice of edge. Prim's algorithm, we started with a choice of vertex and then picked the edge of lowest weight starting from that vertex. And I decided I was going to start at A, and it just so happened that one of my cheap edges was there. But I don't have to do that. I can start at any vertex. By default, I'll start at the first. Now, what do I do to work my way through finding cheap edges? All right, there are two steps in the version of Prim's algorithm. First thing we do is we cross out the column of the vertex we chose. Remove all those numbers, replace them with nulls, dashes, whatever you want. And at the same time, put a mark on the first row. So step one, requires me to put a mark outside the matrix. Now, unfortunately, the downside of Prim's algorithm is that you are going to rewrite this matrix for every edge you need. Which is why this is much easier if you do it in code, because then you can do it in a dynamic array. You can just rewrite the array in itself. But we are doing this on paper, and therefore I am going to have to copy over the entire matrix every time. That's preliminary step. Now we're going to do the loop. From now until we run out of edges and columns and rows. So from I equals 1 to n. Take the rows with the stars. Find the smallest element and indicate it somehow. Mark it. Mark the smallest element of all starred rows. Stop if no such element exists. Let us suppose you choose the IJ entry. These are the two steps we loop through. We're going to do this over and over and over and over again until we run out of elements to circle. So, there's only one starred row. Find me the smallest element in it. What number do you get? 5. So, we take that 5 and we circle it. I'll do that up here. But really, I should be doing this in the new version of the matrix. That's step 2. We've selected the smallest. If you chose Dij, circle that entry. Check. Mark row J with a star. What row do I star? Star the 4th row. And I remove all other elements in column 4 other than the circle. So what's the new version of my matrix? Well, now my new 4th column looks like this. Everything else about this matrix stays the same. Inside the matrix, and outside the matrix, we now have another star. I have two possible rows to select from. What is the smallest number in either row 1 or row 4? Because the numbers in row 4 are 9, 15. Oh, wait a second. I have a 6 there, don't I? I got to be careful. So it turns out that the smallest number I want is the 6 in row 4. Make me a new copy of the matrix, right? Now you see why the dynamic version would come out. You could just cross out some of the things that are already in here and put another star on. But if I do it over and over on the same matrix, by the end of it, you're like, where did all this come from? And it doesn't look very understandable. So, again, me being the pedant that I am, I get a new version of this matrix. Okay, wait a second. What column do I delete the entries from? What row gets a star? Reese? The column where I circled the number, that should be the only number left in it. And that row number for that column, which happens to be the 6th, is going to get my new star. Now you see why when I write the new version of the matrix, I write it by column, because then I don't have to change anything until I get to the 6th column where I just put a circle, since there's already a circle there, and that's the only number circled in that one. Here, there's my most recent circle. I have a star on 1, a star on 4, and now a star on 6. Do it again. But notice now I'm making connections. That edge 5 connects the first vertex with the 4th vertex. This vertex 6 connected the 4th vertex to the 6th vertex. See how they were adjacent to each other? That's what prim requires, that I build off of adjacent behavior. By selecting from starred rows and guaranteeing that I am going to either hit 1 or 4 or 6, and that's where the ends of these edges are, 1 to 4 and 4 to 6. What's my lowest weight on those 3 starred rows? Now it's the 7, Jonah. Okay. What new star shows up on the outside? Row 2, because now I've connected vertex 1 and vertex 2. One, 2 is the new one, 4 and 6. 1, 2, 4, 6, find me the lowest number. I got to redraw it. 3, 4, 5, 6, 7. 7, 1, 2, 3, 4, 5, 6. Okay, what happens to everything else in that column? Say that again, Cole? Exactly. So there's a dash here, a 7 circled, and then everything else is a dash. I already have the circled element in that column. And I had 1, 2, 4, and 6. Where's my new star? Number 5. Wonderful, wonderful, wonderful. Is there a lowest element in 1, 2, 4, 5, or 6? Lauren? The 5 in row 5. Here we go again. Nope, that one's going to get dashed out. So now I have dashes on everything except that 5 that you pointed out to me, Lauren. Where's my new star go? Row 3. So in any row except the last row, what's the smallest number remaining? The only number that is in a row that is smaller than anything else that's not circled. That's my new number. Technically, I get another star, right? Because you put the star at the end of the killing out of everything in that column. That was the row number 7 should now have a star. All my rows have stars. So now I say, hey, what's the smallest non-circled element? What's my smallest non-circled element? At which point I know I can break the algorithm. That's my fault condition. As long as there's still the smallest element available for me to pick. I need to pick it. There isn't one. I'm done. Did you copy down the picture of the graph that I was writing at the beginning? You now know which edges to use. Draw the minimum spanning tree. What's its weight? You don't even need the drawing to know the weight. The weight's just the total of those numbers. Weight's 39. In this case, we get exactly the same tree we got last week. All three versions. The two versions of Prim and Kruskal's algorithm gave me the same minimum spanning tree. That's not a guarantee. As a matter of fact, the only time you can have a guaranteed minimum spanning tree that will be the same every time is if every edge weight is different. But we had repeated weights here, so we might not have gotten the same tree every time. There's something nice about this tree. I just wish I knew what it was. And literally, I have no clue why you got the same one for all the algorithms. I can draw it even from the empty vertex set. Let's see, it was A, B, C, D, E was across, F was down, G was down below. So this edge goes from where to where? This edge goes from A to D. This edge this edge this edge and this edge. I've drawn the tree from the matrix. I got the weights directly from it too. Is this short? No. Is it deterministic? Absolutely. Is it completely non-visual? Yes. And it doesn't require me to do anything other than search for a minimum element under indicated rows, alter my matrix to fit. By making this version, this is not just codable, it's easy to code. And as such, this is more often the preferred method for doing Prim's algorithm. Now, I did start this entire thing with a choice. What was step one? I defaulted crossing out the first column and indicating row 1. I chose vertex A. You don't have to. The book I got this out of said you did have to, but you don't. You could start by lining out any column and marking that row. Because in a simple graph, every edge shows up off the diagonal and will therefore show up in a different row from column. So no matter which column you take out, all those edges appear in some other row, not on the diagonal, because it's a simple graph with no loops. I ate it. Where's my other written example? Is this it? Yes. This was our other graph from Monday a week ago. Ready? Now this time, I'm only going to write the matrix once. We're going to speed run this time. We'll do it in dynamic programming style. So let's start with a 6x6 matrix. And instead of using infinities, I'll use a null, a dash. You could use any symbol you want to say you can't get there from here. I'll null it out instead of using an infinity. You want to use an infinity, that's fine. 1 dash 4 1 dash. B to B, B to C, B to D, B to E, B to F. C to D. So here is my starting matrix. My distance matrix, D. How many times am I going to go through my loop? Because I am getting a minimum spanning tree on 6 vertices. Tree has to have n minus 1 edges. My default was to start with vertex A. I'll do it again. Line out column A. And put a star on that row. Find me the smallest entry in the starred row. You have a decision to make. Because you can either use the one in the second column or the one in the fifth column. It's your tie-breaking mechanism. Last time I picked the smaller alphabetical one that came earlier in the alphabet. You could pick the one that's on the right. You could pick the one that's on the left. It doesn't matter. If I stick with my tiebreaker from before, I go there. What's my dynamic step? What's the next thing that happens? And notice again, I have a tiebreaker here, right? You need to pick a 1. But there's a 1 in the first column, the first row, and a 1 in the second row. You can use either one. Doesn't matter. Me, which one do you want to use? The top one. Everything in that column goes away, and that's 1, 2, 3, 4, 5. So now I add row 5 to my list of acceptable rows. Notice I've prevented myself from making a cycle. How? What did I do that forcibly removed cycles from consideration here? And it would have worked regardless of which one I picked. I took out all the other options available to go from E back to A or B when I chose those columns. And now, by indicating that row, my cycle has been prevented. I can't return to a column I've already used. I can't make a cycle. I have to do it visually. I physically am constrained against it. All right, lowest number now. Rows 1, 2, and 5. You get a tiebreaker again. Regardless of which one you use, you're using one of the 2's in column 3. 2 here, a 2 here. Those are in starred rows. There are no 2's up there. There's nothing smaller anywhere else. Top or bottom? And now, row 3 gets a star. Between rows 1, 2, 3, and 5, what's my smallest number? 3. Which 3? Again, I have a tiebreaker. I have 2 3's that are available. Abigail chose the top one. Kill out the rest. That's the 6th column, so row 6 gets a star. There are only 2 uncircled numbers, yes? The tied. And regardless of which one you pick, the number in question is in column 4, which will put a star on row 4. Everything will be starred. I will have selected 5 edges. I know I will be done with my loop. For the record, I think in my notes here, I picked the other 4. Does it matter? Not in the slightest. You would have the same minimal weight. You'd have the same weight for a spanning tree. You wouldn't necessarily have the same tree. You'd have the same lowest weight. Which in this case is what? 4, 9, 10, 11. There we go. Which is the same weight we got with Prim and Crustle last week. I want you to understand that's why I copied the matrix down every time, because if I just gave you this, you'd be like, what the just happened? Just seeing this end product is not enough. I can't run myself as a GIF so that you can rewind and watch it over and over, but that's what the video is for, and that's why the step through the other version works. There are dozens of minimal and maximal algorithms just like this. If we'd started in a different place instead of row column 1, we should end up in the same place. The worst of all possible worlds would be if we happened to pick a row or column that only contained high numbers and started with that one. So if I were to say, I'm going to start with column 4 and then row 4, well, then I'm going to get stuck with one of these 4s, yes? But notice that's either column 1 or column 5, and all of a sudden I'm connected back to things that have 1s. So even in the worst case in this graph, you'll end up with a minimal tree because I end up with the minimal edges I can get to. But that does make this a greedy algorithm. You can only get to what's nearby. You can't look at the overall picture. Kruskal's algorithm allows me to look at the overall list of edges, even if I have to jump from place to place to place to place within my graph. Whew. Questions? There is a proof in the textbook for each of these algorithms that proves you get a minimum spanning tree. If you believe me, you don't have to read it. But if you're going to go into networking or computer hardware or even potentially cybersecurity, it might be worth understanding why this gives you the lowest results. Unfortunately, this is a proof by contradiction. So it isn't a direct, intuitive, one-way setup. And that's because of the need to eliminate cycles. There are several other algorithms we will do later in the semester whose matrix versions are easier than the words descriptive, visualized versions. I'm a visual person. I really like seeing this in pictures. I found this version of Prim's algorithm, this made so much sense. And it prevented me from having to hunt through cycles by hand. Can't. You literally cannot make one. Okay. The minimum spanning tree problem is one of a set of cost problems, weight problems in graph theory. There are also other questions about connectivity and about taking graphs apart and looking for subgraphs within them. I will come back to other connectivity algorithms, but I want to take a diversion into how to take graphs apart. That is what we will start on Wednesday. I will see you all then. Have a wonderful rest of your day. If you have questions about the exam, I did post the key immediately after I finished grading it. Look at yours, look at that, come talk to me. I hope it has now reduced your stress for the next exam. I will see you all.